Welcome to our online chemistry class. Myself, Mukesh Kharge from SSPMS and Junior College, Shivajinagar, Pune 5. Our topic is chemical kinetics. Let us discuss part number 2 of this topic. In this part, we are to discuss integrated rate law. So, let us discuss integrated rate law for first order reaction. Consider the first order reaction in solution first. So let us suppose our reaction is A, which is the reactant, gives product. Then all are familiar with the rate law of any reaction. So rate of the reaction is directly proportional to the concentration of that reactant. This is your rate law. We write here differential rate law for first order reaction. Rate is equal to minus d dt of concentration of A. d dt means it is the differential form of change in concentration with respect to change in time, and this is very short, small change, and here the negative sign indicates that the concentration of A decreases and passes, and it is equal to K into concentration of A. Here power of the concentration of A is 1, so it is a first order reaction, where square bracket A represent concentration of that reactant A at time t. This is our first equation. If we rearrange this first equation, then what we get? Rate is equal to transfer the concentration of A to left hand side, it goes to denominator instead of that dt, and dt will take the position of A on right hand side. So our rate becomes, and transfer the negative sign also to right hand side. So d concentration of A divided by concentration of A, which is equal to minus K into dt. This is our second equation. Now we have to integrate this, but for that purpose we have to integrate within some limit. So let us suppose that A0 represent the initial concentration of that reactant A when your time is 0, t is equal to 0. Suppose that AT, so t suffix is it represent the final concentration of A at time t is equal to t. Now we have to integrate the above equation number 2 between the limits of concentration of A from A0 at t is equal to 0 to concentration of A is equal to AT at t is equal to t. Substitute this limit and integrate the above equation 2. We can write integration from A0 to AT dA upon concentration of A, which is equal to minus K, which is constant, so taking outside the integration, and integration of dt from 0 to t limit. Now if we integrate this, so you must know some rules of integration of 1 upon x dx, which is log to the base e, and integration of dx is nothing but x. So if you use these formulas, then you can easily integrate this equation. Then what we get? So log to the base e can be also denoted by ln. So ln a, write down the limit, lower limit is a0, upper limit is at, which is equal to minus k, integration of dt is t, and limit is 0 to t. So if we substitute these limits, and then what we get, first substitute the above limit, upper limit, minus substitute the lower limit. So ln at minus ln a0, which is equal to minus kt minus minus plus k into 0, that means 0. So only kt's remain on right hand side. Now if we rearrange this, then what do we get? All of you know about the rule of logarithm. Log a upon b is equal to log a minus log b. So same rule we have to apply here. Ln at minus ln a0 is nothing but log at divided by a0. Right hand side is same. Then this is equation number 3. If we multiply this with negative sign, then right hand side minus minus become plus. Kt is on left hand side minus ln at upon a0, which becomes, if we multiply that negative sign, then it becomes a0 upon at. Or if we check the previous equation, ln at minus ln a0, if we multiply this equation, then it becomes minus ln at minus minus become plus ln a0, that is nothing but ln a0 upon at. And again transfer the t to left side, then what is our k? K becomes 1 upon t ln a0 upon at. Okay, now here ln means log to the base e. If we change the base to 10, then we have to multiply the equation by a number 2.303. So our equation becomes k is equal to 2.303 upon t log to the base 10 a0 upon at. This equation number 4 gives the integrated rate law for first order reactions. With the help of this integrated rate law equation, we can determine the unit of k, which is the rate constant for first order reaction. So in logarithm term, two concentration terms are involved and there is a division. So the unit of concentration, that is mole per dm cube, get cancelled, and in the remaining equation only t is the term at denominator whose unit is second, minute or hours. So write the reciprocal of that. So our unit for rate constant is second inverse, minute inverse or hours inverse. This is about the unit. Next one is the graphical representation of first order reaction. So for that purpose you must write the different forms of your first order equations. So let us consider this equation. So how will you write? Log of a0 upon at to the base 10, it is equal to, transfer this 2.303 upon t to this side, then what do we get? It becomes kt upon 2.303. okay, and if we multiply with negative sign, then it becomes minus kt upon 2.303, which is equal to minus log to the base 10 a0 upon at. And if we multiply that negative sign to this logarithm term, then numerator becomes denominator, denominator becomes numerator. So what do we write? Minus kt upon 2.303, which is equal to log at upon a0. Then that is nothing but, on right hand side, log at upon a0 means log at minus log a0. Transfer that a0 to left hand side, then what do we get? And we can write in terms of log at. Our equation becomes log to the base 10 at is equal to minus kt upon 2.303 plus log to the base 10 of a0. Now this equation can be written in the format of y is equal to mx plus c. So log to the base 10 of at is nothing but y. It is placed on y axis. Your t time is on x axis. Then m means minus k upon 2.303 and this plus log a0 to the base 10 is nothing but c, which is the intercept on that y-axis. And if you plot a graph in between log at with time t, we get a inverted straight line. Why there is an inverted straight line? Because there is a slope with negative sign, so that's why it is inverted, and it touches on that y-axis at this point, and the distance from 0 to that point is nothing but the intercept c log a0 value. So this is one graphical representation. It is wrongly shown in your textbook on page number 128, so make it correct. And similarly you can plot a different graphs of one graph is variation of rate with concentration of A, that is initial concentration, or you can check another graph here also. Log to the base 10 a0 upon at is equal to kt divided by 2.33. so if you plot a graph of that log of a0 against t, then you can observe the line and tell me in the comment box where you observe that line. Okay, so this is about the graphical representation. Then next one is half-life period and rate constant of that first order reaction. So first of all we will discuss what is the half-life reaction. Okay, it is denoted by T half. So it is nothing but the time taken for a reaction when half of the starting material has reacted, or it is the time required when half of the reactants get consumed. That is nothing but the half-life of that reaction. So let us consider this graph. If we plot a graph of concentration of that reactant against time, let us suppose when time is 0, then the concentration of your reactant is 20. Okay, concentration of reactant is 20. When it reaches to 10, means half of that initial concentration of that reactant, then the how much time will be required to changes from concentration of A is equal to 20 to 10, and that time is nothing but the half-life period. Similarly, this is the first half-life period, and again when your concentration changes from 10 to half of it, means 5, then that time is the second half-life period of your reaction. So in this way you can calculate the half-life period. So half-life period is denoted by T half. So the integrated rate law or rate constant for first order reaction is equal to K is equal to 2.33 upon T log to the base 10 of A0 upon AT. So K is nothing but the rate constant or specific rate reaction. Then A0 is the initial molar concentration of the reactant A at time t is equal to 0. When it falls to AT, then time becomes T. Now for first order reaction, the time required for A0 to becomes A0 by 2, means becomes half, then the time is called as half-life period denoted by T half, or you can write when T is equal to T half, AT becomes A0 by 2. So substitute these values in the above rate law expression, then K is equal to, so 2.33, substitute T by T half, then log A0 becomes A0 as it is, AT becomes A0 by 2, because at that time initial concentration becomes half, and that is your final concentration when T becomes T half. So if we solve this, 2.03 upon T T half log A0 upon A0 by 2. A0 get cancelled. Denominator of denominator becomes numerator. So what is your term? Log 2 to the base 10. If you take the log, the value becomes 0.3010. If you multiply it by 2.303, your answer is 0.693, and at denominator T half. If you rearrange this, so T half is equal to 0.693 upon K, which is the half-life period of first order reaction. In this formula, the concentration of your reactant is absent, so your half-life period is independent of initial concentration. So this is the half-life period. Then when time question may be asked, write a short note on first order reaction with example. So which are the examples of first order reaction? 2N2O5 gas gives 4NO2 gas plus O2 gas. Or another example is 2H2O2 liquid gives 2H2O liquid plus O2 gas. These are two examples, or it may be asked in multiple choice question. These examples having dash order. So these are the first order reactions. Now next is the integrated rate law for gas phase reactions for first order reaction. So for that purpose, we have to consider the reaction in gaseous phase. A gas gives B gas plus C gas. Let us suppose that Pi represent the initial pressure of your reactant A at time t is equal to 0. As reaction proceed, when time becomes t, your initial pressure of your reactant A decrease by a value of x. Then when time t passes, then you have to calculate the pressure of your reactant as well as product B and C. So at initial stage, your product is not present in the reaction mixture, so the initial pressure of B and C is nearly equal to 0 or exactly 0. Now we have to calculate the pressure of this ABC when time t passes. So from initial pressure Pi, the x amount of pressure will decrease of that reactant. So what is the pressure of A at time t? It is Pi minus x. Okay, and the x pressure of B and C is generated. So Pb, which is equal to Pc, which is equal to x respectively. Now with the help of these pressures of reactant and product, we can calculate the total pressure P of your gaseous mixture at time t. So P is equal to Pa plus Pb plus Pc, which is equal to, substitute the values. Pa is nothing but Pi minus x, Pb is equal to x, and Pc is also x. So if we add them, and what we get? Pi plus x. Okay, that is the value of total pressure, and from this value we can calculate the value of small change in pressure. X is equal to P minus Pi. Okay, now if we substitute this value of x in the pressure of A after time t, then Pa is equal to Pi minus x is equal to P minus Pi. So what we get? Pi minus P plus Pi, which is nothing but 2Pi minus P. Okay, now our integrated rate law for first order reaction, K is equal to 2.303 upon T log to the base 10 concentration of A0 upon AT. So here we take the solution for your reaction. Reactants and products are expressed in terms of their concentration. Now if you take the gaseous phase reactions, these concentrations of the reactants at initial stage and at time t get replaced by pressure term. So what is A0, which is the initial concentration of A, replaced by initial pressure of your reactant, which is equal to Pi. At is nothing but the concentration of A at time t, which is replaced by Pa, which is nothing but the pressure of A at time t, which is equal to 2 Pi minus P. So if you substitute these values in equation 1, then what we get the equation K is equal to 2.03 upon T log to the base 10 Pi upon 2 Pi minus P, which is the integrated rate law for first order reaction in gaseous phase. So this is about the integrated rate law for first order reaction in solution and gas phase. Now, so meantime, in your board exam, the question may be asked, derive the integrated rate law for first order reaction. Okay, so in previous board exam, only solution of the reactants and products are given, but in this new syllabus, the gaseous phase reaction is also included, and the rate law is also given in your syllabus. So you have to prepare both these integrated rate law equations. Okay, so this may be asked for 3 marks. So prepare this question, derive the integrated rate law for first order reaction in terms of solution or in terms of gaseous phase. These are 2 separate questions. Now we go for next point, that is the integrated rate law for zero order reaction. So first of all, what is the meaning of zero order reaction? So if the rate of reaction is independent on the reaction concentration of your reactant, or when power of the concentration of reactant is 0, then that reaction is zero order reaction. So consider the zero order reaction. A gives product. The differential rate law for zero order reaction is independent on reactant concentration. So rate is equal to minus ddt of concentration of A, which is equal to K into concentration of A raised to 0. This 0 represents it is a zero order reaction. So anything raised to 0 is nothing but 1. So which is equal to K into 1, which is equal to K. This is your equation 1, where A is nothing but the concentration of reactant A at time t. Okay, so if we rearrange this equation, your rate becomes dA is equal to minus K into dt. Now let us suppose that A0 is the initial concentration of reactant A at time t is equal to 0. Suppose that AT is the final concentration of your reactant A at time t is equal to t. So our above equation number 2 can be integrated within the limit A is equal to A0 at time t is equal to 0, which is the lower limit, and the A is equal to AT at time t is equal to t, which is the upper limit. So integration of dA from A0 to AT, which is equal to minus K, which is constant, from integration of dt from 0 to t. So if we integrate this, integration of dx is nothing but x, and integration of dt is nothing but t. So what is the on integration value? So dA on integration gives A from A0 to AT, which is equal to minus K, which is constant, into t from 0 to t. We substitute the limit, and what do we get? So substitute upper limit minus substitute the lower limit. So AT minus A0 is equal to minus KT into 0. Okay, so if we rearrange this, so if we multiply the equation with negative sign, what do we get? Minus AT minus minus plus A0, which is equal to plus KT. So you can write KT is equal to A0 minus AT. A0 minus AT. If we transfer this T to right hand side, so K is equal to A0 minus AT upon T this equation number 4 is nothing but integrated rate law for zero order reaction. Okay, remember this formula. So if you observe this formula carefully, at numerator the concentration terms of your reactants are given, and at denominator the time is given. So when you calculate the rate constant for zero order reaction, so the subtraction of concentration has one unit, which is mole per dm cube or mole per liter, and which is divided by time. So time in second. So what is the unit for rate constant? It is mole dm raised to minus 3 second raised to minus 1. Okay, so this is your unit. Then graphical representation of zero order reaction. So if you observe the equation number 3, you can write that equation 3 in another form, transferring the AT to left hand side, KT to right hand side. What is your equation? AT is equal to minus KT plus A0. Again, this equation in the format of y is equal to mx plus c. So y is nothing but AT. That value is placed on y axis. X is nothing but t, which is placed on x axis. So if you plot a graph of AT against t, then we get a straight line, but inverted straight line. Why? Because your slope is minus k, which is negative value. So it is inverted line, and it touches to your y axis, that gives the intercept. So this point to 0 is nothing but the intercept on y axis, and that is a0 value. So this point to 0 value means a0 value, which is the intercept. This is the graphical representation of zero order reaction. Then half-life and rate constant of zero order reactions. So the rate constant for zero order reaction K is equal to A0 minus AT upon T. So when T is equal to T half, your concentration at time T is equal to half of its initial concentration, which is equal to A0 by 2. So if you substitute this value in this equation of rate law, then K is equal to A0 as it is. AT is nothing but A0 by 2 divided by T is nothing but T half. So A0 minus A0 by 2 is nothing but A0 by 2, and T half is as it is. Okay, so if we change the K and T half, so transfer the T half to left side, K to right hand side. So T half is nothing but A0 upon 2K. So if you observe this formula of T half, that is the half-life period, here concentration term is involved. So half-life period of zero order reaction is directly proportional to initial concentration of your reactant A. Remember this, it may be asked in multiple choice question. Half-life period of zero order reaction is directly proportional to initial concentration of reactant. And what do you say about the first order reaction? Write down in comment box. Okay, we already discussed. So then examples: 2N2O gas gives 2N2 gas plus O2 gas in presence of platinum. So decomposition of nitrous oxide in presence of platinum. This is the first example. Then second example is pH3 gives 4 times pH3 gas gives P4 gas plus 6H2 gas, and this reaction is nothing but the catalytic decomposition of pH3 on hot tungsten at high pressure. So this is the second example. Third example is decomposition of ammonia gas on platinum metal. So 2NH3 gas gives N2 gas plus 3H2 gas in presence of platinum. So in this example, if you observe, the metal surface, which is the platinum, get completely covered by a layer of ammonia molecule. The number of ammonia molecule attached on platinum surface is small as compared to total number of molecules of that ammonia. So a large number of ammonia molecule tends to remain as gas which do not react. They remains unreacted, and the molecule present on the metal surface which can react. And these molecules are very few in number. Therefore, the rate of reaction was thus independent on the total concentration of ammonia. So, as this concentration is independent, its concentration of ammonia remains constant. So, we can say that the rate of reaction is independent on the concentration of ammonia. So, it is a zero order reaction. Okay. So, sometime question may be asked, what is zero order reaction? Explain with example. So, you can write this example. Then, another question is, derive the integrated rate law for zero order reaction. So, these questions are separate, or sometime 2-mark question is, derive the half-life period and rate constant relation of zero order reaction, or derive the half-life period and rate constant of first order reaction. These questions may be asked for 2 marks. Okay, so these are few questions which may be asked in previous board exam. Now next point is zero order reaction that we already discussed. Now we have to discuss pseudo first order reaction. So what is the pseudo means? False. So the reaction which is expected to be higher order but follow first order kinetics, that is nothing but pseudo first order reaction. So certain reactions which are expected to be higher order but they follow first order kinetics. And what is the reason behind this? If there are 2 or more reactants in your reaction, and if one of the reactant is in large excess, then we suppose that that reaction is higher order, but actually it follow the first order kinetics. So let us consider one example, that is hydrolysis of methyl acetate, which is ester CH3 COO CH3 in aqueous react with water. Hydrolysis means addition of water in liquid state, which is in excess form, gives acetic acid CH3COH aqueous plus methyl alcohol aqueous. So the rate law for this reaction is rate is equal to K dash into concentration of methyl acetate CH3COH into concentration of water. So this reaction was expected to follow the second order kinetics, but here water in this equation is present in large excess. Therefore, the concentration of that water is taken constant, which is equal to K double dash. So our rate law equation becomes, or rate law expression becomes, rate is equal to K dash into concentration of methyl acetate into concentration of water is K double dash. So K dash into K double dash is nothing but a new constant K. So rate becomes K into concentration of CH3 COO CH3. So here in final rate law expression, only the concentration of methyl acetate is present. That means the rate of reaction is depends on concentration of methyl acetate, and it is independent of concentration of water. So here in rate law expression, only one reactant is involved, so it follows the first order kinetics. Okay, so many time question may be asked, what is pseudo first order reaction? Explain with suitable example. Another example is given, sucrose C12H22 Co11. It also undergo hydrolysis in presence of excess of water gives C6H12O6, that is glucose in aqueous state, plus C6H12O6 fructose in aqueous state. So can it be of pseudo first order reaction type? So here water is taken as excess. If it follows the first order kinetics, then it is pseudo first order reaction. So I think all of you understood the pseudo first order reaction. Answer for the second equation is it follow the pseudo first order kinetics. Okay, so these are the two examples. So remember these examples. Meantime question may be asked, identify the order of the given example in multiple choice question. So this is about the chemical kinetics. Thank you for watching my YouTube channel Mukesh Kharge. If you like these videos, you can subscribe and share my YouTube channel Mukesh Kharge.